In this video, we are going to learn how we can derive new Taylor series from ones we already have by substitution and by using algebra. So there's a few different things I can do to take a Taylor series that I already know and get a new one. So for example, we've seen this Taylor series for sine of x before. In fact, this one's centered at x equals 0, so it's what's called a Maclaurin series, just a special Taylor series. And what I'm going to do with this is I'm going to replace this x with just an x squared. I'm going to sub it in. So I got to do that same thing on the polynomial side. And if I plug in x squared, I'll get first x squared, and then minus x squared cubed will be x to the 6th over 3 factorial, and then I'll get x to the 10th over 5 factorial, and so on. That next up I'll get a minus and dot, 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 because this alternates. And I got the Taylor series for sine of x squared. I can also do algebra on a Taylor series to get a new one. So if I needed to do sine of x squared divided by x, well, on this side, I'm going to divide all the terms by x. And that'll give me x minus x to the 5 over 3 factorial plus x to the 9 over 5 factorial minus dot, dot, dot. Okay, so that's really nice. If I have a Taylor series that I already know, or Maclaurin series, I can just substitute to get new ones and also do algebra like this, like divide or multiply, add, subtract terms. I can also do the derivative or antiderivative of an existing Taylor series, which we'll talk about in a later section. One of the cool facts about Taylor series is that they work with complex numbers as well. So I want to end by looking at an example. I want to find the Taylor series for e to the ix, centered at x equals 0. So remember that I is our imaginary number. It's the square root of negative 1. And we've seen this Taylor series of e to the x before. It's centered at x equals 0, so it's a Maclaurin series. And if I substitute and I replace the x with ix, I'm going to do that with all the x's on this side. So then I have to put a ix over here, and then next I'll get this ix squared, and then ix cubed, ix to the 4th, and then so on. And if I simplify these, well, the first two terms, I'll just keep them as they are. But then when I have ix squared, I squared, that becomes negative 1, because when I square this, it gets rid of the square root. So that's why I have this minus, and then I get this x squared. I cubed, well, I cubed is I times I squared, and I squared is negative 1, so this is negative I. So that's going to give me this negative, and then there's still an I there, and then x cubed. When I do I to the 4th, well, that's going to be I squared, which is negative 1, getting squared. That's going to be positive 1. So that's why for this I to the 4th one, I to the 4th just becomes this positive, and then the i's are completely gone. I just have this x to the 4th. And then I could keep going. The 5th term would be this, and the 6th power term would be this. And one of the things that I notice is, well, some of the terms have i's, and some of them don't. And I'm going to highlight each set. So all the real terms, so the ones that don't have any i's, are these even power terms. And the ones that have i's are these odd power terms. I'm going to highlight those. And if I rearrange this and separate the even power terms from the odd power terms, it's going to give me the even power terms. I'll get 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. After that, it would have been a plus dot, 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 because they're alternating. Okay, and then with all the terms that have an I, what I'm going to do first is factor the I out. So if I factor the I out, factor the I, and then I'll put a parentheses. So what's left over from this first term is just x over 1 factorial. From this next term, I'll get minus x cubed over 3 factorial. And then from this 5th power term, I'll get plus x to the 5 over 5 factorial. And then after that, it'll be minus dot, dot, dot. And now each of these things in the parentheses, they're actually the Taylor series for some known function, some function that I already have. I want to have you give the video a pause for 1 minute and see if you can recall what functions they represent. In 3, 2, 1, pause it and try that. So the even power one, that's just cosine x. And this one with the odd powers, that's sine x. So what this has shown is we started with e to the ix. I'm going to write that down, e to the ix. And it equals this cosine x plus I times sine x. And this is, we've derived one of the most important formulas in math here, actually. This is something called Euler's formula. This is Euler's formula, and it relates exponential functions involving complex numbers with trig functions. That's kind of remarkable. In our later sections, we'll take a look at how we can actually use this to derive a bunch of identities.